Dear students, after studying this module, you shall be able to know what is mass spectrometry, learn the principle of mass spectrometry and its instrumentation, analyze the various types of mass spectrometers available, identify molecular ion peak and evaluate a mass spectrum. Now, let us introduce this module of the instrumentation of mass spectrometry. Mass spectrometry is an analytical technique used for the determination of masses, or I should say relative masses of the molecular ions and their corresponding fragments by the calculation of the amount of deflection of the charged particles in the presence of an external magnetic field. It provides a great deal of information with very small amount of samples. Mass spectrometry is used to determine molecular mass, molecular formula of a particular compound. It is also used to determine structural features of many compounds, and it is used to find out the structure of a compound, also to provide data on isotopic abundance and verify the identity and extent of purity of a known substance. Mass spectrometry is an instrumental technique that does not involve electromagnetic radiation. Thus, it is called spectrometry, whereas others such as UV, NMR and IR are called spectroscopy. Thus, I hope you can understand what is the difference between spectroscopy and spectrometry. Spectroscopy is a technique which uses electromagnetic radiation. However, spectrometry is a technique which does not use electromagnetic radiation. Other organic type and inorganic type of compounds, in order to segregate ions by their charge to mass ratios and also their qualitative and quantitative detection by their M by Z values, mass spectrometry is also used for such purposes. The M by Z values are also very helpful in finding out the relative abundances of many isotopic patterns of compounds. Now students, I would like to tell you the order in which the mass spectrometry is carried out in the instrumentation. The initial step involves the production of gas phase ions of the compound by a beam of energetic electrons. Deduction of an electron from a particular molecule M results into the generation of a parent ion. Let us say it is denoted as M plus. Now it is also known as a molecular ion. The parent ion's M by Z value is equal to the mass of that compound. Now you can see in this reaction how the molecular ion or the parent ion is generated. Now you can see apart from the plus sign, there is also a dot which is there on the M plus. Now what is that? It indicates the presence of a radical cation which is formed. That is called a molecular ion. Now the parent ion M plus is an entity which contains odd number of electrons which can yield a radical R dot and an ionic species with even numbered electrons, that is E1 electron plus, that is EE plus, or a molecule N which is neutral and a new radical cation QE plus and with a dot to represent the radical in it. Now as you can see here how the molecular ion gives an even electron ion or an odd electron ion. The even electron ion comes with the radical and the odd electron cation comes with a neutral molecule N. This is shown in the figure or the equation that you can see here. Further fragmentation processes of ions derived from the molecular ion can also be observed, students. All species of these ions formed are then separated by the mass spectrometer according to their respective M by Z ratios. Only positively charged species reach the collector. The charge Z on all the fragments is +1. Therefore, students, M by Z is equal to the molecular mass M of the fragment. A plot of the relative abundances of each of the respective fragments is known as the mass spectrum. For example, in the case of methane, that is CH4, the impact of high energy electrons causes the molecule to lose an electron and form a radical cation with the m by z value of 16. Now, a species having an unpaired electron and a positive charge is known as a radical cation in this case. Now, you can see here in this equation how a radical ion or cation is formed from the methane gas after the bombardment with a energetically active beam of electrons. Now, you can see after the beam of electrons is put on the methane, how the fragments are formed with the mass 15, 14, 13 and 12 respectively. And thus, you can obtain clearly a mass spectrum of methane where m by z is plotted on the x axis and the relative abundance of various fragments obtained after the bombardment with electrons is obtained on the y axis. And you can see what is the ratio of relative abundances of the fragments obtained in this case also. Now, let us begin students with the instrumentation of the mass spectrometer. The mass spectrometer contains basically three components: sample, inlet and ion source. We are going to take that up together. Mass analyzer and ion detector. Now, for your ease, we have shown you before the beginning, before the brief introduction, we have shown you the diagram of mass spectrometer here. You can see how there is a sample inlet and an ion source. Then there is a mass analyzer in the middle, and then you can see the detector, and after that this whole instrument is connected to the computer, from which you can obtain your mass spectrum in the form of a bar graph. Now, let us discuss about sample inlet and ion source, which causes the ionization of the sample involved. A sample studied by mass spectrometry may be a gas, a liquid or a solid. A sample inlet system provides this stream of molecules. With gases, as the substance is already vaporized, so a simple inlet is used in this case. The inlet system is only partially evacuated, so that the ionization chamber itself is at a lower pressure than the sample inlet system. The sample is introduced into a large reservoir from which the molecule of vapor travels through a small pinhole, also called a molecular leak, before entering into the main chamber. The same system can be used for volatile liquids and solids. For less volatile materials, the system can be designed to fit within an oven, which can heat the sample to increase its vapor pressure. With non-volatile samples, other sample inlet systems must be used, and a common method is the direct probe method. The sample is placed on a thin wire loop on the tip of the probe, which is then inserted through a vacuum lock into the ionization chamber. The sample probe is positioned close to the ion source. The probe can be heated, thus causing vapor from the sample to be evolved in proximity to the ionizing beam of electron. A system such as this can be used to study samples of molecules with vapor pressures lower than 10 raised to power minus 9 millimeter of mercury at room temperature. The most versatile sample inlet system students are constructed by connecting a chromatograph with the mass spectrometer. This sample introduction technique allows a complex mixture of components to be separated by the chromatograph, and the mass of each of the separate component can be successfully determined individually. So, you can understand how mass spectrometry is so useful for organic chemists who study mixture of compounds and they need to obtain a pure compound from it. The instrument should be capable of obtaining at least one scan per second in the range of 10 to 300 m by z values. So, the initial step students involves evaporation, as I told you, of a small amount of compound. This is then followed by the ionization of the vaporized sample by bombarding it with a beam of high energy electrons. Now generally this is 70 electron volts. Now this electronic beam emitted takes out an electron from the molecule from the sample, which is then injected, thus creating a molecular ion or a radical cation, which I have discussed already in this module previously. The molecular ion thus formed further breaks into fragments as it travels through the mass spectrometer, as loss of electron weakens its bonds and collision gives it an extra kinetic energy. The positively charged one causes the positively charged radical cation to accelerate into the analyzer tube. Now the energy required, students, for deducting an electron from the neutral parent molecule is usually 8 to 15 electron volts, and this value is often referred to as the ionization potential or the ionization energy of a particular compound. With this much energy, the parent ion does not undergo fragmentation, but the energy of the bombarding electron is around 70 electron volt. This additional energy, apart from 8 to 15 volt of ionization energy, is consumed in fragmentation of the parent ion. As a result, fragment ions are formed from the daughter ions. Now let us discuss ionization methods in organic mass spectrometry. Irrespective of the method of sample introduction discussed earlier, once the stream of sample molecules has entered the mass spectrometer, they must be converted to charged particles by the ion source before they can be analyzed and detected. There are many types of ionization methods available with their own advantage and disadvantage. The ionization method used depends on the sample type under investigation and the instrument which is available. Now let us take a detailed look into the various ionization methods. Most of the ionization methods create both types of charges, that is positive and negative, depending upon the proton affinity of the sample which is employed. In positive ionization mode, the protonated molecular ions, that is M plus H, whole of the positive charge, are generated. In negative ionization mode, the deprotonated molecular ions, represented as M minus H negative, are usually generated. Now students, let us take a look on the first method of ionization, is the electron impact ionization. This is the simplest and the most common method for converting the sample into ions. In EIMS, I will use this as a short form for electron impact ionization mass spectrometry. A beam of high energy electrons is emitted from a filament that is heated to several thousand degrees Celsius. These high energy electrons, they strike the stream of molecules that has been admitted into the sample inlet system. Now this electron molecule collision strips an electron from the molecule, which creates a cation. A repeller plate which carries a positive electrical potential directs the newly created ions towards a series of accelerating plates. This creates a large potential difference ranging from 1 to 10 kilovolts apparently across these accelerating plates, and this produces a beam of rapidly travelling positive ions. One or more focusing slits direct the ions into a uniform beam. EIMS has distinct advantages over routine mass spectrometry for all small molecules of organic compounds. Electron ionization hardware is inexpensive and robust. This is one great advantage of EIMS for small organic molecules, and the excess kinetic energy imparted to the sample during the EI process, it leads to a significant fragmentation of the molecular ion. That means it leads to more information which is required for the detection of new information about an unknown molecule. The fragmentation of the molecular ion under EI conditions may also be considered a distinct disadvantage. Some compounds fragment so easily that the lifetime of the molecular ion becomes too short to be detected by the mass analyzer and detector. Thus, one cannot determine a compound's molecular mass in such cases. Now, this is another disadvantage. Another drawback to EIMS is the sample must be relatively volatile, so it can come into contact with the electron beam in the ionization chamber. The fact, coupled with the fragmentation problem, make it difficult to analyze high molecular weight compounds and most biomolecules using EIMS. Now, here you can see a nice diagram of electron impact ionization and all the parts of such an instrument. Here you can see filament, repeller plates and accelerating plates. Now, let us come on to the second part and second way of ionization in mass spectrometers, which is called chemical ionization. Students, in chemical ionization, the sample molecules are combined with a stream of ionized reagent gas that is present in great excess relative to the sample. When the sample molecules collide with the pre-ionized reagent gas, some of the sample molecules are ionized by various mechanisms, including proton transfer, electron transfer and adduct formation. Almost any readily available gas or highly volatile liquid can be used as a reagent gas for chemical ionization mass spectrometry. Now, here you can see all the parts that I have already mentioned in the figure for chemical ionization mass spectrometry. We shall now come on to some very important ionization techniques which form a group, also known as the desorption ionization techniques. Now, let me tell you which all techniques fall under desorption ionization techniques. First of all is the fast atom bombardment, that is also short form as FAB. Second is the matrix assisted laser desorption ionization and is popularly called MALDI. Secondary ionization or ion mass spectrometry, also is short form as SIMS, is the third category of desorption ionization techniques. In these desorption techniques, the sample to be ionized is dissolved or dispersed in a matrix and placed in the path of high energy, that is 1 to 10 kilo electron volts beam of ions in case of SIMS, neutral atoms in case of FAB, or high intensity photons in case of MALDI. Beams of argon or cesium are often used in SIMS and beams of neutral argon and xenon atoms are commonly used in FAB or FAB-MS. Most MALDI spectrometers use a nitrogen laser that emits at 337 nm, but some applications use an infrared laser for direct analysis of samples contained in gels or thin layer chromatography plates. SIMS and FAB ionization methods may be used on sample compounds with molecular weights up to about 20,000, such as polypeptides and oligonucleotides. The matrix should be non-volatile, relatively inert and a reasonable electrolyte to allow ion formation. Common matrix compounds for SIMS and FAB include glycerol, thioglycerol, 3-nitrobenzyl alcohol, di and triethanolamine and mixtures of dithiotritol, that is DTT, and also dithioerythritol. MALDI mass spectrometry is useful for analytes spanning a wide range of molecular weights of a few thousand atomic mass units to oligosaccharides, oligonucleotides and polypeptides, antibodies and small proteins with molecular weights approaching up to 3 lakh AMU. Now, furthermore students, MALDI requires only a few femtomoles of the sample. Now, you can imagine with such small amount of samples, still it will give the correct mass. So, how important it is for organic chemists. Now, you can see here the combined techniques, that is multi-SIMS and FAB-MS techniques, as I have compiled them in this figure. Now let us come to the fourth ionization technique, also known as the ESI ionization, that is electrospray ionization technique. An even more useful technique, that is ESI, for studying molecular weight of biomolecules and other labile or non-volatile compounds is electrospray ionization and its cousin technique thermospray ionization. In ESI, a solution containing the sample molecules is sprayed out at the end of a fine capillary into a heated chamber that is nearly at atmospheric pressure. ESI has become the most common technique in the past 2 decades for use as an LC-MS systems. ESI-MS is not only limited to the study of large biomolecules. However, many small molecules with molecular weight in the range of 100 to 1500 can be studied by ESI-MS also. Compounds that are too non-volatile to be introduced by direct probe methods or are too polar or thermally labile to be introduced by GC-MS methods are ideal for study by the LC-MS using the ESI techniques. Now students, after having finished with the ways of ionization and the sample inlets, let us come to the study of mass analyzer. The segregation of various ions occurs in the analyzer at a pressure amounting to 10 to 8 millibar. A curved magnetic field surrounds the analyzer tube, which deflects the path of the radical cation in proportion to its mass to charge ratio m/z. The factors on which the flight path of an ion depends upon are its charge, its molecular mass and the strength of the magnetic field applied. Hence, at a specified magnetic field, the ions having specific masses collide with the detector and thus they get recorded and thus we obtain a mass spectrum. Just as there are different ionization methods, there are varied analyzer methods also for varied applications. The first one is the magnetic sector mass analyzer. In this type of analyzer, the ions are passed between the poles of a magnet. In the presence of a magnetic particle, it describes a curved flight path. The method would not be very interesting if the ions of only one mass can be detected. Therefore, the magnetic field strength is continuously varied, called a magnetic field scan, so that all the ions produced in the ionization chamber can be detected easily. Now, you can see here how there is a scan of magnetic field in the figure and there is an entrance and exit slit in this magnetic field analyzer. Second in this is the double focusing mass analyzer. Magnetic field analyzers are used today only in double focusing mass spectrometers. The particles leaving the ionization chamber do not have precisely the same velocity. So, the beam of ions passes through an electric field region before or after the magnetic field sector. The particles describe a curved path in each of these regions and the resolution of the mass analyzer improves by a factor of 10 or more over the magnetic field sector analyzers. Next, we come on to the quadruple mass analyzers. A quadruple mass analyzer has typically a range of 0 to 1000 m/z values and the corresponding spectrometers are low resolution instruments, that is R is approximately 3000, which are incapable of providing exact elemental composition of the sample. It works on similar principle as the linear quadrupole. Now, you can see here how this quadruple mass analyzer looks like in this figure. Next, we come on to the time of flight analyzers. These analyzers are based on a simple idea that the velocities of two ions created at the same instant with the same kinetic energy will vary depending upon the mass of the ions, that is the lighter ion will have a higher velocity than the heavier ion. In theory, time of flight mass analyzers have no upper limit to their effective mass range and these mass analyzers have high sensitivity. The major disadvantage, however, students, of the TOF analyzer is its inherently low resolution. The mass resolution of the TOF instrument is proportional to the ion's flight time, so longer drift tubes increase the resolution. Now, you can see in this figure here what we are trying to explain you about the TOF mass analyzers. Now, let us move on to the study of ion detectors. The ions which are separated by the analyzer are detected and measured electrically or photographically. Post the passage of the ions through the exit slit, they collide on a collector electrode. The current which results is thus amplified and registered as a function of magnetic field force or the accelerating voltage. The magnetic field strength is varied in increments to give a mass spectrum, which is a plot of m by z on the x axis against the relative abundance on the y axis. On the basis of the assumption that all the ions possess a charge of +1, the peaks provide the mass ratios and their corresponding heights provide the proportion of the ions of different masses which are obtained in the mass spectrum. Now, you can see here in this figure different types of detectors which I have just talked about. Now, students, let us go on to the combined study of detectors, analyzers and ionization methods and see how they make up different types of mass spectrometers instruments as a whole. Depending on the methods of ionization, ion separation and detection described in detail above, there are various types of mass spectrometers which are shown. Now, you can see here, according to the ionization technique, there can be electron impact ionization, electrospray ionization, chemical ionization, SIMS, MALDI, FAB, etc. And in case of ion separation, there can be quadruple, magnetic sector field, electrical sector field, time of flight, ion trap, etc. In case of ion detection, there can be electron multiplier, multi-channel plate and a Faraday cup which are used. Now, a combination of these is used for creating different instruments of mass depending on the utility of the user who is conducting the experiment to find out the mass of the unknown or known organic compounds. Now, let us come to the study of analysis and separation of sample ions through the mass spectrometer. The function of utmost importance in a mass analyzer, students, is to separate or resolve the ions formed in the source of ionization of the mass instrument according to their own mass to charge ratios. Now, there are a number of mass analyzers currently which are available, as I have already discussed above, the better known of which include the quadruple magnetic sectors, electric sectors and time of flight analyzers, and both Fourier transform sector and the quadruple ion traps. Now, let us move to the study of tandem mass spectrometers. These are instruments that have more than one analyzer, so they can be used for structural and sequencing studies of molecules. 2, 3 and 4 analyzers have been incorporated into commercially available tandem instruments, and the analyzers do not necessarily have to be of the same type because the usage of each analyzer is different, and in which case the instrument becomes a hybrid one. More popular tandem mass spectrometers include those of the quadruple, magnetic sector quadruple, and more recently known is the quadruple time of flight geometries, which can help in detection of different aspects of a particular molecule. Detection and recording of the sample ions. The detector monitors the ion current, amplifies it, and the signal is then transmitted to the data system, which is recorded in the form of mass spectrum. Now, this I have already told you that after the detector has detected the ions, the m by z values of the ions are plotted against their intensities to show the number of components in the sample, and the molecular mass of each sample and their relative abundance can be known from this bar graph. The type of detector is supplied to suit the type of analyzer. The most common ones I have already stated is that the electron multiplier, the multi-channel plate and the Faraday cup. Now, you can see here in this figure, why I have told you these things again is that it shows you the history behind the development of various mass spectrometer instruments which have been available in the market, and how technology has progressed and shown us better ways into detecting more molecules with better instrument technologies. Now, rapid improvement in various technologies has led to the development of better mass instruments, which helps a chemist certainly in detection of unknown compound and confirmation of the known compounds and their formation. Now, this diagram actually aptly describes the historical development of mass spectrometry techniques, and it also makes you or makes one appreciate how much effort has gone into designing and making the technology more suitable year after year, so that the chemist can do better work and prove better to the society. Now, students, it is the time to evaluate a mass spectrum after having studied in detail the instrumental techniques. Now, we will see here in particular the fragmentation of pentane. Pentane is an acyclic hydrocarbon. The study of a mass spectrum requires prerequisite knowledge about the nominal molecular mass, the m by z value, molecular ion peak, base peak and other peaks obtained upon fragmentation. The m by z value is a nominal molecular mass of the fragment, and it is the molecular mass to the nearest whole number. For example, students, pentane has a molecular mass of 72.0939 AMU and a nominal molecular mass of 72 AMU, that is, we have round off this figure, that is the nominal molecular mass. Pentane undergoes fragmentation between carbon-carbon bonds to form various radical cations with different m by z value. Weaker bonds break off more easily as compared to stronger bonds, and the bonds which break form more stable fragments in comparison the bonds that form less stable fragments. Now, you can see the probable fragments which are formed on the splitting of the molecular ion of pentane, and that here is obtained as a spectra which can be seen here as bar graph or in tabular form. Now, you can see the mass spectrum of pentane, and you can see how the relative abundance of the molecular ion peak as well as the various fragment is obtained in case of pentane. And there is a table also which shows you the m by z values versus the relative abundance of molecular ion peak as well as the fragments which are obtained at different values. The peak with the highest m by z value is 72 in the spectrum of pentane is due to the fragment that results when an electron is knocked out of the molecule. It is also known as the molecular ion peak, as I explained you in the very beginning of this module, and is equal to the molecular mass of pentane. Peaks with m by z value less than 72 are called the fragment ion peaks. The peaks at m by z 43 with the greatest intensity is called the base peak. Thus, students, I would like to state here that the correct elucidation from the mass spectral data can help an organic chemist to a great extent to show and to know about the lot of information about a known or an unknown organic compound. Now, students, let us summarize this module. Mass spectrometry is an analytical technique used to determine for the masses of molecular ions and their corresponding fragments by the calculation of the amount of deflection of the charged particles in the presence of a magnetic field. The instrument contains an ion source, mass analyzer and an ion detector. The vaporized sample is then ionized by bombardment with a beam of high energy electrons, usually which is 70 electron volts. The initial step involves the evaporation of a small amount of compound, followed by the ionization of the vaporized sample by bombarding it with a beam of high energy electrons, generally 70 electron volt. This electronic beam takes out an electron from the molecule of the sample, which is injected, thus creating a molecular ion or a radical cation. The segregation of the ions takes place in the analyzer. The ions which are separated by the analyzer are detected and measured electrically or photographically. The m by z value is the nominal value of molecular mass of the fragment and the molecular mass to the nearest whole number. Mass spectra can be depicted either as plots or in tabular form. Peaks with m by z values less than parent ion are called fragment ion peaks. The peak with the greatest intensity of all is called the base peak. The various ionization methods are electron impact, chemical ionization, fast atom bombardment, electrospray ionization and matrix assisted laser desorption ionization. Various types of mass analyzers include quadrupoles, magnetic sectors, time of flight analyzers, electric sectors and both Fourier transform and quadruple ion traps. The common types of detectors are the electron multiplier, the multi-channel plate and the Faraday cup detectors. Students, I hope you found this module very interesting.